a remote outpost in Western Germany, home to NATO's main operating base. This specialist crew from around the world are constantly on alert. Their job, to spot hostile intrusion as they protect state borders that span the Northern Hemisphere.
The military are permanently on the lookout for different types of threats from all around the world. Hostile craft are in the air, on land, on sea, and they can come from all different directions. And without cutting-edge technology, protecting and defending is impossible. Hostile aircraft in particular are masters of camouflage because they can fly out of sight in valleys or behind mountains, and they can fly incredibly fast and low, all without being detected. The fundamental challenge for the military is to detect threats early so that they can react quickly and, if necessary, defend.
For over a century, engineers have been coming up with ingenious ways to improve military surveillance. During World War I, massive concrete structures were used to listen out for the enemy. But often it was too little, too late.
Oh dear.
Then along came radar, and by the 1930s they could see for miles. But only if nothing was in the way. More and taller towers were built to increase the area covered. But no matter how tall or how many were built, it was never enough. Modern-day engineers have now taken radar technology to the next level: the skies. This is AWACS. One of the planet's most sophisticated surveillance aircraft. Able to seek out, locate, and defend against threats, no matter how fast-moving or well hidden.
This is a massive and highly sophisticated machine. It's carrying 4.7 tons of ingenious technology on its back. 7.6 tons of equipment in the body of the plane. That's a staggering 12.3 tons of specialist equipment. And it's airborne.
The technology behind this amazing aircraft is kind of magic. It's just a tremendous piece of engineering.
This aircraft is like no other, able to see threats not only in the air, but also at sea. Operated by a specialist crew of engineers and technicians, surveillance experts, and weapons controllers. Beneath the crew lie state-of-the-art signal amplifiers, the nerve center of this aircraft's most unique feature. An enormous 9-meter rotating radome, housing a 1 million watt radar system, with a scanning range of 300,000 square kilometers, an area larger than Arizona.
You are clear on engine number 2, target process. All right.
The AWACS technical supremacy also enables it to function as a flying command post for large and complex missions.
This incredible machine can be used to coordinate up to 150 aircraft at one time, and that's what makes it so extraordinary. There has never been an aircraft with this capability in military history. It's an impressively fast and accurate way of keeping the airspace safe. When the AWACS is in the air, nothing and nobody can hide.
Today, the crew have been scrambled to investigate suspicious activity due south. They'll be airborne for 12 hours.
Traffic 330.
AWACS is an incredibly complex piece of aviation equipment. The machine itself is awesome. The number of pieces that interplay is almost beyond comprehension.
And all the groundbreaking technology that's been added enables AWACS to carry out the most complicated of missions. But creating a machine like this poses massive challenges.
So how do you mount this huge radar system on the back of an aeroplane? how do you protect against a threat that's invisible? And once in the air, how do you stay there for as long as possible?
There's so many aspects of this aircraft that you would normally find spread over a huge area on the ground there. Nowadays, it is all in one plane. It's an incredible aircraft.
On the ground, engineers are working 24/7 on the AWACS fleet.
The aircraft is vital to the Alliance here. We can do air battle management and various other activities. So the commanders regularly request AWACS support. It's an incredible aircraft.
But when you're flying over 800 kilometers per hour at 10,000 meters high, ensuring the radar system functions properly is full of challenges.
In order to put this vast radar system onto a plane, the first problem is the sheer size. All that power and equipment that would normally be in a large radar tower is now going on an aircraft. On the ground, you have plenty of space for your generator and cooling mechanism, but in the air, you simply don't.
As well as the size, the Radome must be stable enough to withstand wind, vibration and temperature, and the stresses of taking off and landing.
The Radome also needs to allow the radio waves to pass through it, so there can be no internal structure that would compromise the signal.
For such complex engineering, inspiration was needed from pioneers of the past. The first long-range radar arrays were planted firmly on the ground. British radar systems throughout World War II were mounted on huge and heavy 110-metre towers. To come up with a solution to the problem of strength versus weight, engineers found inspiration in outer space. Kate Mulcahy is at London's Science Museum, looking at one of mankind's greatest achievements.
And here it is. This is the Apollo 10 command module.
Orbiting the moon 31 times. This is the actual command module from NASA's 1969 lunar program. This three-crew mission to the moon and back was the dress rehearsal for the lunar landings that followed, and pushed engineering to the limits.
On its way back to Earth, the command module actually set the record for the fastest speed in a crewed vehicle at 39,897 kilometers an hour.
NASA's engineers had to build a spacecraft that could withstand the challenges of the 1 million kilometer lunar mission.
They had to build a module so that it was light enough to get to space in the first place, but it also had to be rigid and strong so that it could withstand the stresses of re-entry as well as deceleration forces of up to 6.7 G. And finally, it had to not buckle or collapse when it actually landed. And I can see part of the solution here. This is a honeycomb lattice that's sandwiched between two thin outer layers.
In 1638, Italian astronomer and scientist Galileo Galilei observed how honeycomb-type structures in bird bones increased strength without adding weight. The principles observed in nature inspired engineers to build their own honeycomb structures.
These sheets of paper clearly aren't very strong, but if I'm to take these same sheets of paper and instead use them to make tubes like this, if I then take the tubes of paper I've made and I attach them all together, I get a honeycomb type structure. Now, if I add a sheet top and bottom, what I'll end up with is a sandwich.
The exact same amount of paper that was once flexible is now rigid.
Now, the facings on this sandwich take the bearing load. That's the compression and the tension. And the honeycomb takes the shearing load. This structure is incredibly strong. Not only can it carry one brick, but actually it can carry much, much more than that.
Honeycomb sandwiches allowed NASA to meet the criteria of strength, rigidity, and low weight.
This can easily take 7 bricks. In fact, it could probably take more.
But engineers still faced the biggest challenge of all. On re-entry to Earth, temperatures would reach over 2,700 degrees centigrade, hot enough to melt most metals. The honeycomb was made of 370,000 individual cells. Epoxy resin was injected into each cell by hand. Engineers calculated the resin would melt in such a way that heat dissipated away from the inner structure.
Considering this was such a new technology, I can only imagine the thoughts of the crew as they were finally making their journey back to Earth.
3, 2, 1, set.
The ultimate test came as the module approached the Earth's atmosphere.
Hello, Houston, Apollo 10. We are returning to the Earth. Over. Glad to have you on the way back home, 10.
On the module's heat shield, the resin had burnt away, leaving layers of honeycomb and the inner structures perfectly intact.
It's amazing because this honeycomb sandwich not only saved the mission, but it also saved the lives of the crew inside.
Thanks to the honeycomb sandwich technology, 11 modules successfully made the hazardous journey through Earth's atmosphere and back to Earth over the course of NASA's lunar program. The NASA team had achieved the impossible. To create the AWACS radar system, engineers have taken honeycomb technology and combined it with state-of-the-art radar. The whole of the radome structure is formed from honeycomb, making it light enough to piggyback on a jet plane. Lieutenant Colonel Jens Meyer oversees the radome's maintenance.
I got some honeycomb material here. Let me just show you what this really is made of. Very flexible, very lightweight. This type of material, the honeycomb structure here, you can put an 85-kilo soldier on this and it will not move one bit. When you put layers of fiberglass on top of it, it also becomes very inflexible, so you have a very sturdy while lightweight structure that can withstand very strong forces.
The strength of these layers that form the radome means no internal bracing is needed. And the shape of the honeycomb allows radar signals to pass through the structure, uninterrupted and without distortion.
Without the honeycomb structure, it would have been impossible to manufacture the Radome as it is today.
Okay, let's have a look at the antenna. So we are going close, forward.
Engineer Roger Snyder services the radar assembly.
Okay.
The radome's interior is the heart of AWACS. Only seen by the qualified few.
Up front, you see a motor who turns the antenna. It's a hydraulic motor. This makes it possible that the antenna is spinning at 6 rotations per minute. Up here, you have 3 receiver protectors and just below, low noise amplifiers.
But powering this million-watt system provides engineers with a further problem.
One challenge in transmitting at that high power, of course, is the heat that is generated by the transmitter. Therefore, we are cooling and stabilizing the temperature with fluoride carbonate, and therefore having a very stable temperature, what is important for the antenna to work as designed.
High temperatures inside could also cause the radome structure to distort, obstructing the radio waves. So the honeycomb's impregnated with a resin mix that helps maintain the radome stability during temperature changes. It's the perfect environment for radar transmission.
We are able to work and pick up targets with less noise, therefore achieving a higher range.
Octane 5-8, Magic loud and clear.
Such a highly sophisticated cooling system is the only reason AWACS is able to achieve its mission.
33,000, passing from west-east.
It's an extraordinary and seemingly impossible feat of engineering. With the Honeycomb cooling and radar equipment in place, AWACS can survey 360 degrees across an area of 300,000 square kilometers.
One of the challenges involved with monitoring large areas is staying in the air long enough to gather all the information that is needed. To maintain a tactical advantage, you must be able to gather enough data, and the longer the AWACS can stay at altitude, the better the air and sea pictures that it can provide.
AWACS can fly for up to 8 hours, but for some missions, pilot Micah Redfield may need to remain in the air for longer. The trouble is, the fuel consumption is dictated by the load he's carrying.
So we can take anything from 5,000 or 10,000 pounds to 100,000 pounds if there was a mission that really dictated that much on-load. So people in the past have been trying to solve the problem of air refueling in order to extend that mission duration and be able to provide better capability.
So how do you keep a 93-ton military aircraft airborne beyond its fuel capacity? For the answer, engineers look to one of history's greatest aeronautical inventions. Since we first flew, pilots have attempted to stay airborne for as long as possible. In 1920, a pilot tried to pick up a petrol can from a float. In 1921, a wing walker tried carrying a can of petrol from one plane to the next.
Imbecile!
And in 1923, pilots used a line to lower a petrol can to a plane below. All these attempts have been as dangerous and unreliable as they sound. In mid-30s Texas, Al and Fred Key were desperate to find a solution to achieve their goal, breaking the world record for the longest ever non-stop flight. They were flying a Curtiss Robin plane called Ole Miss.
Push the mixture in. Throttle is set. Area is clear. Hit the starter.
Pilot Andrew Keast flies one of the few remaining Curtiss Robin planes.
Grab some fun. What's special about this airplane is it's a beautiful and graceful airplane as it flies. It's in its own class.
The Key brothers knew the Curtiss Robin would be the best plane to help them rewrite the history books.
The tubular design of the Curtiss Robin was a very strong design, so they were able to put a very large fuel tank in the back of the airplane for this endurance flight. And the structure of the fuselage was strong enough to support running boards on both sides of the airplane, and the pilot and mechanic would be able to go out and service the engine, change spark plugs, change oil, all during flight without having to shut it down and land.
The Key brothers had the perfect plane. Now they needed to work out how to refuel without stopping. The ingenious plan they came up with seemed simple enough. Spare fuel would be carried by a plane above, and a fuel hose would be lowered to the Curtiss Robin below. But mid-air refueling for real was to prove an almighty challenge.
I can't make it any better than that.
A fuel hose without a weight to steady it was lethal. Back on terra firma, Andrew's simulating in-flight conditions.
Here's an example of just a line with no stability device on it and how unstable it is. You can imagine what this would look like at 80 miles an hour.
Previous attempts had proved unsuccessful. Fred Key was hit in the face by a hose, and another pilot snared and dragged to his death as he struck the propeller. They had to figure out how to stop the fuel hose spinning dangerously out of control.
So the Key brothers looked into aerodynamics to find a way to stabilize the fuel hose, and one of the things they come up with was a basket they put on the end of the hose to stabilize it.
Andrew's going to test the cone-shaped device the brothers came up with.
Okay, here we go for a test. So coming through 10 miles an hour, it's lifting off the ground. There's 20 miles an hour. Well, it's flying and it's just holding in there nicely. It's just very stable. 20 miles an hour, it's working.
Equipped with cone-shaped aerodynamics, at last the fuel hose could be managed safely at altitude and at speed. On June 4th, 1935, the Key brothers set off on their record-breaking attempt. With mid-air refueling mastered, the Key brothers were able to receive more than 6,000 gallons of gasoline. The brothers achieved an astonishing world record. They flew their Curtiss Robin non-stop for 653 hours and 34 minutes. 27 days in the air.
Key brothers were definitely aviators of the day. They truly were test pilots. They helped engineer aerial refueling. It's a major thanks to engineers and early aviators that really paved the way to what we have today.
Modern mid-air refueling rigs use aerodynamic designs pioneered by the Key brothers.
And you're established.
Copy.
The probe and drogue system is the industry standard.
As technology has progressed, that has developed into the probe and drogue system. So having essentially a parachute at the end would stabilize the movement of the hose system, and the drogue became a much more effective tool.
Chain 42's disconnected. And he's off to the right.
Despite the proven technology of the probe and drogue system, refueling AWACS is a much bigger challenge for pilot Micah Redfield.
A heavy aircraft like the AWACS is not as maneuverable as a smaller fighter might be, because the AWACS just simply isn't capable of maneuvering quickly enough to use a drogue-style traditional system.
We won't be able to see him, but he's coming back soon. Copy that.
Engineers had to take the refueling system to the next level, a remote-controlled flying boom. Approaching the tanker plane, Micah must use the utmost skill.
The pilots will proceed visually up to get within 50 feet of the tanker initially.
Maybe to the left?
Yep. Perfect.
At that point, the pilot will stabilize the aircraft and try to neutralize any aerodynamic forces that are affecting the aircraft.
40 feet. 30. 20 feet. 10 feet.
flying on full manual control at 500 kilometers per hour, just meters below a tanker filled with fuel, is one of the riskiest maneuvers Micah will ever have to face.
It does become quite complicated, and it's a very physically demanding skill for pilots to develop. It is something that takes a lot of concentration and effort.
Clear for contact.
Off to the right.
The boom operator is sitting in the back of the tanker aircraft, and they have a joystick that can actually fly winglets on the boom to move into position.
Six one contact.
I'm bumping. Copy.
With an incredible 3,700 litres of fuel being pumped into the AWACS per minute, the crew are all on high alert.
The system has always been an inherently dangerous problem. There's a bit of nerves every time you go up, but you still have to be very conscious of what you're doing and what you need to do to execute safely.
Having safely docked and received thousands of litres of fuel in midair, AWACS is ready to go.
The people who pioneered air refueling were incredible aviators and also just incredible human beings. They were figuring it out all for the very first time. It was really amazing what they were able to do, real pioneers of aviation.
On top of the plane, the 9-metre rotordome houses a 1 million watt radar assembly. The radar ancillaries and cooling systems extend through the fuselage and wings. Inside, 3 technicians, 5 surveillance crew, and a tactical director manage the data. The radar system enables AWACS to see an area of 300,000 square kilometers below.
The radar is delivering a lot of raw data. It's being processed onto the screens for the individual to actually assess whether an aircraft is a friendly, is a foe, whether it's a fighter aircraft, whether it's just a transport aircraft. They provide a consolidated air picture for the commanders on the ground.
But it's the invisible threat that causes the most destruction.
One of the major challenges when designing the AWACS is how to keep the aircraft flying during a nuclear war. In the event of a nuclear explosion, electromagnetic pulses are released that can disable some of the sensitive equipment on board, rendering it completely useless.
So how do you keep AWACS safe from an invisible enemy? To find out, engineers had to look back at the biggest bomb blast of its time. In July 1962, the US carried out the Starfish Prime nuclear test.
Starfish Prime was launched and was entirely successful.
Exploding a 1.4 megaton bomb 400 kilometers above the Pacific Ocean.
A tremendous amount of data was recorded during these events.
The blast caused a sudden and rapid acceleration of charged particles, called an electromagnetic pulse, or EMP. Similar to a bolt of lightning, the pulse was so powerful it destroyed electrical components over 1,000 kilometers away.
We do need more information on this fireball blackout.
With the threat of nuclear war still around today, AWACS must be protected from the destructive effects of EMP.
Okay, sign says off limits to non-essential personnel, but I've got permission, so let's take it through the gate and see what's behind it.
Dan Dickerell is visiting a top-secret US Air Force facility to find out more.
It doesn't look like anyone's been here for years. Weeds are growing up through the road. What an amazing place. So this place is really off limits. No one gets to come here. I've heard about it, and oh, there it is. That thing is huge. That is something else.
In the 1970s, engineer Dr. Carl Baum built an EMP test facility at Kirtland Air Force Base in Albuquerque, New Mexico.
All right. Let's go have a look.
Decommissioned and out of bounds since the early 90s, the site is still a masterpiece of engineering.
Oh, wow. This massive structure is 1,000 feet long and 125 feet high, and it's the world's largest structure made entirely of wood and glue. It's called the Atlas Trestle.
Built at a cost of $60 million and constructed with 6.5 million board feet of lumber, the trestle was strong enough to support a fully loaded B-52, then the largest and heaviest bomber in the US inventory.
Aircraft would taxi down 1,000 feet to the end of the trestle, perched above the ground as if it were in flight. Once we were in position, two massive generators on either side would unleash a 200 gigawatt pulse in less than a millionth of a second. That energy would be directed down these transmission wires. This pulse would simulate the EMP generated by a nuclear explosion.
The engineers knew how to generate EMP, but the bigger challenge was simulating its effects in flight.
Now, the ground can affect the EMP readings, but also the trestle itself, the structure. So the solution to this was to create the entire thing out of wood, no metal at all. These giant, large timbers, even the nuts and bolts are made of wood, and I have an example of one here. The wood is impregnated with a phenolic resin. It makes it very strong, but also EMP transparent. The combination of all of these solutions meant the EMP results would not be affected.
With the trestle itself shielded from interference and the EMP generators working at the optimum configuration, engineers could apply stress to specific aircraft components and so determine how to best protect flying planes from nuclear attack.
So the solution looks something like this. Here I've got two phones. I'm going to call this phone from this phone. As I dial my number, what we'll see is the radio waves go from this phone to the mobile tower, transmitted through the atmosphere, and here we see the phone call is being made. So it works. What I can do now is I can trick this phone into not receiving the call. So I'm going to take this phone and I'm going to wrap it in this fine wire meshing. This phone is now safely encased. Okay, so let's try this again. I've got my phones. When I make the call this time, I'm going to listen. The call is being made. The radio waves are going through the atmosphere, but the receiving phone is not ringing.
The trestle engineers were using a principle first devised in the 1830s.
So we had constructed a Faraday cage. Now, how does that work? Well, in the atmosphere, we have electromagnetic waves that are traveling through, in our case, radio waves for the cell phone transmission. If those waves encounter a barrier where the holes in that barrier are quite small, smaller than the wave itself, the wave cannot penetrate that barrier and is forced to go around. So the wave can't pass through the barrier because the hole is too small. And this principle is the same principle that is used to protect aircraft from the harmful effects of atmospheric EMP. By testing certain planes and seeing how the energy dispersed across its wings and fuselage, the data gathered could be applied to other planes' designs as they evolved.
Many plane designs benefited from EMP testing, making the Atlas trestle one of the great secret engineering feats of the 20th century. Engineers have applied everything learnt from the past to create AWACS.
They actually designed this aircraft being a big flying Faraday's cage here. So the fuselage made out of metal there, that will route all the energy around the precious electronics in the inside.
AWACS is engineered to be the most EMP-resistant plane possible. An aircraft structure designed and built to withstand and redistribute electrical charges. Door seals fitted with EMP-conducting gaskets. But the EMP proofing doesn't stop there.
All the cabinets inside the aircraft are also smaller Faraday's cages here, protecting all the electronics inside even further.
And the sensitive radar equipment is shielded too.
There are also filters in the lines from the antennas, filtering out whatever spikes of electromagnetic energy is coming through there.
But there's still one more challenge: the plane's windows. Glass doesn't stop EMP, so the windows are laced with a fine wire mesh. The holes are smaller than the electromagnetic waves, so they won't pass through it. And the crew can see out.
Left, you can do 180 left, easy, inbound CP.
Okay. 100.
The runways is set.
Yep. 50. 40. 30.
The mission today has analysed a huge amount of data to build a clear picture of activity across the Mediterranean, in and out of North Africa. The classified information has been relayed directly to Allied NATO forces.
Excellent, Data 1-1.
No wonder AWACS has been declared the most significant single tactical improvement since the advent of radar.
It's incredible how people manage to overcome all these challenges, putting radars in here, electronic systems here, inertial navigation systems. This aircraft is just a tremendous piece of engineering, and I'm actually very glad that I'm allowed to help maintaining it.
AWACS is the jewel in NATO's crown. It is a triumph of the skies and has pushed the boundaries of what man thought possible. It's one of the most impressive radar aircraft ever built. Capable of staying in the air even during a nuclear attack, the AWACS can detect threats and pass on vital data and information to military units on the land, sea and air. Just the fact that a 9-meter diameter rotating radome housing a 1 megawatt radar system can take to the skies is an incredible feat of aeronautical engineering.
A highly modified aircraft, 46 meters long with a wingspan of 44 meters, able to refuel in mid-air. 7.6 tons of equipment in the body of this reinforced machine, capable of withstanding the effects of a nuclear war, and mounted on top a 9-meter diameter rotating radar assembly housing a 1 million watt radar system. AWACS has pushed the boundaries of engineering.
I have to say I love this system. It's one of those aircraft you really have to love as an engineer, because there are so many challenges that had to be overcome by ingenious engineers here. And for me, it's an incredible aircraft.
By drawing on the innovators of the past, adapting, upscaling, and conquering many challenges, engineers have created a plane like no other.
those moments that you can stop and step back as you walk out to an airplane and you see it, and you really appreciate how much has gone into aviation, and you get a little of the joy of why you started flying in the first place. So I enjoy it. It's a great experience.
And its success will be far-reaching.
It has taken decades of innovation. This is a triumph of engineering that has to be seen to be believed.
The AWACS engineers have succeeded in making the impossible possible.